In this video, I wanted to introduce and discuss the Shapley-Shubik power distribution, which is an alternate way of determining the power levels within a weighted voting system. And what I wanted to begin with is, well, what are the differences? Because a lot of the aspects of the Shapley-Shubik power distribution are very similar to that of Bonzoff, if not exactly the same. So the main difference to the Shapley-Shubik method is that we're going to be now caring about the order in which the players are voting. So if you recall about the Bonzoff power distribution, we talked a lot about coalitions and discussing, which of the players within each winning coalition is critical. But we did not pay mind to, well, what order they come in. And it's something I didn't mention at the time, which you may have been wondering is, well, what if the order is different? Does that matter? So, that's really the main difference. In Bonzoff, no, the order does not matter. But in the Shapley-Shubik, yes, the order does matter. And so to introduce a couple of the key terms in the Shapley-Shubik power distribution, um, we have the term pivotal player in sequential coalitions as opposed to critical player in regular coalitions. So everything we talked about last week in 2.1 and 2.2 was more focused on what are the coalitions using the brace notation, and who is critical to those coalitions, which we figured out by underlining them. But what I wanted to really emphasize before we actually got into how we do the Shapley-Shubik and the math behind that is that it's a little bit different, and all those terms are super similar. But basically, let's talk about, well, what does a sequential coalition mean, and what is a pivotal player? How do we define that? So a sequential coalition is just an ordered list of all the players in the system. So when we were thinking about the Bonzoff power distribution, we wanted to figure out all of the coalitions that would be considered winning. Which is another way of saying, well, what are the subsets of the players? Like, say, for example, we have 4 players. What if 2 players say yes and 2 players say no? And so on and so forth. But one of the key differences with the Shapley-Shubik method is when we're thinking of the sequential coalitions, we're not going to be doing subsets. We're going to be doing a complete list of all of the players. But instead of thinking about who says yes and who says no, we're going to think about what if they said yes in this order. And so basically in the Shapley-Shubik power distribution, we're just going to use a different notation so that when we're doing math on our paper, or when we're reading the textbook, we can kind of tell, okay, what does this mean? What's the difference? There's no there's no greater meaning to the symbols that we use. Like, just as to recap, we use the bracket for the system as a whole, where we put the quota, then a colon, then a list all the weights. When it comes to Bonzoff, we're talking about coalitions using the braces, or sometimes I just call them the squiggly parentheses, which indicate, who's saying yes in the system. But in the Shapley-Shubik power distribution, we're using this other sort of bracket, which is not a traditional bracket, but it sort of looks like an extended greater than, less than sort of symbol. Well, I guess this one's less than, and this one's greater than. And basically, we're going to list each of the players in the coalition. And basically, we want to consider every single permutation of those players. So, like, for example, if we're looking at one of our previous examples, a system with 4 players, in a sequential coalition, we'd list all 4 of the numbers every time. We're not going to be taking smaller groups. The only thing we want to check is what are the different ways we could arrange those players, which is often referred to as a mathematical permutation. And anyways, then also, so returning back to the term pivotal player, a pivotal player is the first player in that sequential coalition whose vote would pass the motion. So this is the other thing that's important, and I want to make sure I mention it, is what this means is we're assuming players are voting yes in this order. So what we could do is say, well, what if the players vote in this particular order? What would happen? And the pivotal player, or sometimes called the swing voter, would indicate, well, at what point who is important to this chain of events. And basically what we're going to be looking at is what are all the chain of events, and figuring out, well, who is pivotal, counting up all the pivotal counts, similar to how we did the critical counts for the Bonzoff method, finding the total, and figuring out, well, how many times was each player pivotal to the sequential coalitions at the end of the day. So let's return back to the same example. Well, actually, let's just sort of summarize the Shapley-Shubik, and then we're going to go back to that same example to which we solved the Bonzoff power distribution, because another thing that I wanted to do was discuss the differences in, our outcome. What are the types of answers we get, and how does it differ from the Bonzoff method from 2.2? But basically, what I like to say is that it's pretty much the same method. The difference is instead of using normal coalitions and finding critical players, we're using sequential coalitions and finding pivotal players. So step one, make a list of all the n factorial sequential coalitions with n players. So what this mathematical calculation is doing, the exclamation point, remember, has a mathematical meaning, something that we'll come back to in 2.4. But basically, you want to list them all, just as we would with bonds-off, right? With bonds-off, we wanted to list all the winning coalitions. Here, we want to list all of the sequential coalitions. Step two, it says in each sequential coalition, determine the pivotal player. For bookkeeping purposes, underline. So similarly, we're going to find who is pivotal. Now, one notable difference with Shapley-Shubik is there can only be one pivotal player per sequential coalition based on the way that term is defined. With bonds-off, remember, it could have been everyone that was critical or only one player or nobody. It just sort of depended on the coalitions themselves in terms of determining who is actually critical. But with sequential coalitions, there can only be one pivotal player, and there will always be one. It then says to find the pivotal counts, basically count them all up, take the ratio of the individual pivotal counts to the total, where SS is just standing for Shapley-Shubik, and sigma is standing for, well, it's kind of the Greek equivalent to S. Just the variables that are representing how many times was each person pivotal, and then what was their actual Shapley-Shubik power index. And that's what SSPI stands for, Shapley-Shubik power index. In the distribution would be, much like the bonds-off power distribution, the level of power for each player, which is sort of the final answer that we get from this. So there is a way to check your answers as well, which you can do online, and there's a link here in the video. But let's go ahead and switch back to the packet and do an example of calculating a Shapley-Shubik power index for the same question that we did before. So it says calculate the Shapley-Shubik power distribution for the weighted voting system 10, 7, 5, 4, 3. And just as a quick recap, remember this means that our quota is set to 10. We have 4 players, each with votes 7, 5, 4, and 3. So let's go ahead and just do it. So the first step is to find all the sequential coalitions instead. So really in this example, I wanted to mention how do we approach finding them all, because typically there's going to be a whole lot more sequential coalitions than there would be normal coalitions. And this is due to just some basic math set theory, which is what we're going to talk about in 2.4. So we'll get to that. But for now, we'll just kind of find them all through attrition. But basically what I would start with is we're always listing all the players. So one of the obvious options for the order in which the players could vote in would be just the order that they come in, right? Order from greatest to smallest, which is player 1, player 2, player 3, player 4. And remember, we could list this as less than P1, P2, P3, P4, greater than, well, this isn't a true less than or greater than symbol because it's a little bit more extended. But when I draw it, it's kind of like, I'm not being that careful with how I actually draw my symbol. But it's just a different type of parentheses so that we're not mixing it up with all the other meanings that we've established. Anyways, but my point is, how do I make sure I find them all? But one of the methods that I recommend that I think is the easiest way to begin is think about fixing some of them in place and then permuting the other ones. So like in this case, what I like to do is arrange my sequential coalitions based on the first player. So what I would first think about is, well, how many different ways could I arrange these sequences if I fix 7 in place? And basically that would leave me with 5, 4, 3. And another thing is, if we're thinking about how many different ways are there to arrange 3 players, there's always going to be 6, which is, again, math that we're going to talk about in 2.4. But another way you could think about it is, well, what if I fix the first 2 players? What other ways could I arrange them? And if I'm keeping the first 2 the same, notice that there's only one other way of arranging 4 and 3, which would be 3 and 4. And this, again, would be a unique sequential coalition because the sequencing of them matters. Whereas in bonds-off, those 2 would be the same coalition because the meaning would be totally different. That would just mean everybody's saying yes. Where in this case, we're thinking about this means these players are saying yes in this order. And actually, if I was thinking about fixing 7 and 5, that would be the only 2 ways to do it, right? Because there's only 2 people left, only 2 ways to arrange them. And I could also, in the same way, think, well, what if I started with 7 and then I went with 4? I could either do 5 and 3, or 3 and 5. So sort of my method of finding them all is by keeping two of them the same and then, you know, writing the other two in every order that I could. I could also start with 7 and 3, which would leave me with 5 and 4, or 4 and 5. And then I would do a similar approach to finding, well, what are all the sequential coalitions that start with 5, 4, and 3 in the same way. And that should give me all the ones that start with 7, right? Because I fixed 7 and 5, which left me with two other options. I did 7 and 4, two other options, 7 and 3. And that's really it there. I only had three other players to pair with 7. So I could also think about, well, what about each of the sequences that start with player 5? And in the same way, I could say, well, let's fix 2. Let's start with 7 and 5, or 5 and 7. And notice how I'm going in decreasing order. So I'm always kind of picking the biggest option just to keep a semblance of organization with these permutations. But basically, I would start with 7 and 5, or 5 and 7. Then I could do 4, 3, or 3, 4. I could start with 5 and 4. That would leave me with 7, 5. Or sorry, not 7, 5, 7, 3. Or 3, 7. I could also have 5 and 3. And that would leave me with 7, 4. Or 4, 7. And that would give me all the 5s. And basically in each case there's going to be the same number, so I'm kind of arranging them in a very organized fashion so that I could kind of make sure, well, do I have them all? There's going to be 6 different options to start with 7, 6 options to start with 5. There should also be 6 that start with 4, and 6 that start with 3. So if I were to start with 4, I could, again, starting with the largest first, do 4, 7, and then that would leave me with 2 more options of 5, 3, and 3, 5. I could have 4 and 5, which would leave me 7, 3, or 3, 7. And I could go with 4 and 3, which would leave me 7, 5, or 5, 7. And then I could drop down to starting with 3, which would be 3. I could start 3, 7, which would leave me 5, 4, or 4, 5. I guess it doesn't really matter. And also, the order that you write them in doesn't matter at all. It just matters that you find them all. And I've found, basically, in my experience teaching this class, that organization is key to making sure we don't leave any of them off. Like with bonds off, if we forget any of our permutations, the math that we're going to calculate isn't correct because we're not thinking about every possibility. And in this case, there's a whole lot of different ways it could go down. So anyways, that leaves me with all my sequential coalitions. So what's next? Let's return back to the snippet from the book, which said step 1, make a list of all the sequential coalitions, including the 4 players. So step 2 was to, in each sequential coalition, determine the pivotal player. And to recap, we're assuming that players say yes from left to right. The pivotal player will be the vote that passes the motion. So basically, since the quota, and this is going to depend on the quota, just like it did with the bonds off power distribution, we want to know, well, at which point will the motion pass? That person is considered pivotal to that sequence. So like thinking about the primary sequence in order, if player 1 says yes first, they're not going to pass the motion, so they're not the pivotal player. Once player 2 says yes, that would be a total of 12 votes for yes, because they're going in order. And we're basically accumulating as we go from left to right. The second player would have enough votes to pass the motion, so we would say that the second player is pivotal to this sequence, because they would be called the swing voter, or basically they're the person that would pass them if this was a sequence of events. And similarly, in the next coalition, will the second player be pivotal? And really, the next player 3 and player 4, the next couple players, they're not going to matter because the motion's already passed. Their yeses cannot make an impact, and the decision has already been made. That's why the first player is not pivotal, because their vote didn't actually tip the balance, and the last couple players won't matter. So there'll always be one, and the motion should always pass, assuming that your quota is in the viable range that we talked about in last week's lecture. So anyways, so sort of to summarize here, find all the ways to arrange the players. In each one of them, add your way from left to right until you hit the quota. When you hit the quota, underline that player, move on. So looking at the next couple coalitions, 7 and 4, at the point when I hit 4, I will hit 11. That will make it to the quota. So in those sequences, the second player will be pivotal. And same with the last two, is 7 plus 3 makes 10. And remember, you just have to meet the quota. You don't have to exceed. So 10 is enough to pass the motion. Those two would be pivotal. Moving on to the second column of sequential coalitions. Again, adding my way from left to right, 5 plus 7 is 12, 5 plus 7 is 12, 5 plus 4 is 9. So notice in a lot of these first options, the second player was pivotal, but that's obviously not always going to be the case, because sometimes it takes more than 2 people to say yes to make the quota. Like in the case of these ones, 5 plus 4 does not make the quota, so they would need the next player to come along. Same with the ones below. 5 plus 3 is only 8, so they would need those remaining votes. And continuing, I'll go ahead and finish. 4 plus 7 is 11. That is enough. 4 plus 5 is 9. Not enough. 4 plus 3 is 8. Not enough. And in the last column, 3 plus 7 is 10. 3 plus 5 is 8. Not enough. 3 plus 4 is 7. Plus 7 is 14. And 3 plus 4 is 7. Plus 5 is 12. And usually your pivotal players will be somewhere in the middle. They shouldn't be first unless, because that would imply a dictator. And they are typically not last, but it could happen. Again, like usual, depends on the numbers, depends on the quota. Higher the quota, the harder it will be to pass. And anyways, we have now finished finding all the pivotal players. And from here, basically, we do the same exact thing as bonds off. We want to figure out, well, how many times was each person underlined under this methodology? And then how many total underlines were there? Figure out, well, how many times was I underlined out of the total? And so basically that's what we're going to do. We need to count up the number of pivotal players for each type. So basically sigma or SS1 and I'm going to try to use the same notation as the book. SS1 is the Shapley-Shubik or the pivotal count for player 1. And recalling that player 1 is the player with 7 votes, because remember, this is P1, P2, P3, P4, so I'm focusing on counting up how many times 7 was underlined. So we have 1, 2, 3, 4. 7 was not pivotal over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So player 1 was pivotal 12 times. And then kind of do the same thing for everyone else. Well, how many times was player 2 pivotal, who had 5 votes? 1, 2, none there, 3, 4. So I believe player with 5 votes was pivotal 4 times. Then moving on to the player with 4 votes, who is player 3. And then we had player 4, who had 3 votes. So player with 4 votes was pivotal once, twice, thrice, 4 times. And player with 4 votes was pivotal once, twice, 3, 4, and that's it. And just like with bonds off, we want to figure out how many times is each person underlined, add up the total. In this case, that adds up to 24. And remember, since there's one pivotal player per sequence, there should be a total number of pivotal players always equal to the number of sequential coalitions, which is always given by the mathematical formula n factorial, which remember, n is the number of players in this chapter. So basically it's given by the calculation 4 factorial, which is, what that means mathematically is to take that number and multiply by each consecutively smaller number, multiplying all the way down to 1. Or technically, you don't really need to multiply by 1 because that doesn't do anything. But and again, we'll return to why that makes sense later. And basically, each player's Shapley-Shubik power index is then their individual power level divided by the total. So player 1 was pivotal 12 times. We just take 12 out of 24 to get their power level, which is equal to 1/2. Player 2 was pivotal 4 times out of 24, which would reduce by 4 down to 1/6. And player 3 and player 4 had exactly the same power levels as player 2, which are 1/6. Or as I said with the Bonzoff power distribution, a lot of times your homework will ask or will want you to input your answers as fractions or as percentages or whatever. I don't really care, but in this case, player 1 has a Shapley-Shubik power index of 50%. Player 2 is about 16.7%, if we round that off a little bit, as do player 3 and player 4, because they had the same pivotal counts. And again, what was our goal? Our goal was to figure out how much power does each player have in the system. And our conclusion here is, well, player 1 has 50% of the power or the control in this weighted voting system. And players 2, 3, and 4 each have this approximately the same, or exactly the same, 1/6 or 16.7% of the power. And actually, if you compare to all the math we did last week with the Bonzoff power distribution, these answers actually turn out to be exactly the same. Which is, it's not always going to be the same as the Bonzoff due to the differences in these methods, but it should usually give us a similar indication, because the whole point of all this is to figure out how much influence do these people have, these various numbers given the quota, and each method is trying to do the same thing. So the major difference is the procedure is very different, right? We're figuring out a bunch of lists and underlining one per list, whereas with Bonzoff, we're figuring out all the different subgroups and seeing who's needed in those subgroups. So some students prefer to use Bonzoff method, some prefer Shapley-Shubik, and at the end of the day, they're both they're just two different ways of doing the same thing. And really, I wanted to wrap this video up because this is getting way too long with why does this method make sense, and why, what's the concept? But basically, if we return and think about this, think about if I'm voting with my friends and we're trying to make a decision on something to do, like say, or we own a company and we have various votes based on how much ownership we have in the company. We could think about trying to make a change or trying to impose a motion where, let's say, we could have a various different way this could happen. Let's say that for one player, like let's just say I'm player 1, let's say that I really want this to happen and everyone else has not decided. What I could then think about is, well, who do I want to vote, and who should I try to get vote? Like if I was trying to then lobby someone to join my side and sort of say, okay, you really should vote this way, who's going to be important, who should I care about? And understanding the power level can help me to know, well, how influential are those votes? Because as we talked about in 2.1, sometimes the actual numbers of their votes can be a little misleading. But really, when we look at all the sequences, we could think about, well, what if this happens and this happens and this happens? And by looking at all of these, we could think about every single possibility of the order in which players could actually vote and think about who is actually important to each of those outcomes.